When you're drawing derivative curves, you need to pay attention to 4 rules. So the first one, the slope is the derivative's value. So say we have a slope right here that's going up and to the right. Let's call this a slope of 1. That means that your derivative curve is going to look like that. It's going to be at the 1 because this is 1 over 1. Actually, I should probably move this 1 over here to make it perfect. And then negative slope, of course, is going to look like this. Well, this is a negative 1. That'll be 0. And if it's just a flat curve like that, well, then your line is just going to be going along 0. Next rule, minimums and maximums, which are basically just peaks anywhere along the curve. So you have like a parabola right here. This right here, that's a maximum or a minima. So whenever we're taking the derivative of this, let me draw another graph right there. This will be 0 at that same exact point. Call that point 2. Your graph will touch right there. Then the steepness, the steeper the slope, the farther it is from the x-axis. So we can see it's really steep right here, and it's not so steep right there, and it's going up in a positive direction. So what that means is the curve is going to be starting from somewhere up here and going down like that. And this is pretty much the opposite. You can see right here. So it's less steep right here, more steep right here, and the curve is going down, so it's a negative slope. So right here we have positive side and a negative side. So the fourth rule, inflection points are where concavity changes. So say I have a curve that looks something like that, the concavity will change right there at this mark right here. So that means that there will be a minima because it's going negative, right? Like the whole, like along the point of inflection right here, slope is negative, so that must mean that wherever this minima is along the point of inflection, it's going to be below the x-axis. So erase that right there. And then in order to help us plot this, we're going to look at our first rule, 0 slope, which would be right here. Let me get my other pen for that. 0 slope right there, and 0 slope right there. That means that our point is going to be along the x-axis. So we just trace this whole thing. It's going to look something like that. And those are the 4 rules. So yeah, rules are great and all, but I prefer steps whenever I'm drawing a curve, and I'll give you a few tips right here. So the 4-step process to draw a derivative curve: mark the original function extrema and points of inflection. 2, extrema are the points on the x-axis. 3, points of inflection become the extrema. So I should probably specify here extrema of the derivative, right? points of inflection of the original function are the extrema of the derivative. Extrema on the original function are points on the x-axis of the derivative. Right. And then smoothly connect the dots. Simple enough. Some tips. This is just basic calculus. Qubits turn into parabolas. Parabolas become linear. Linears become constant. Sometimes higher order functions can look like a parabola. So x to the 4 could look something like that. It'll have a couple of focal points down there. I'm not even sure if they're called focal points if it's not, or vertices if it's not a parabola, but just be wary of that. So I'll show you an example that should contain everything that we talked about. It'll be, make it really big. All right. So this has pretty much everything in it. First, what we're going to do is we are going to mark our minimas and maximas right there, and then our points of inflection where the concavity changes. So it looks like concavity changes right there. Concavity will change right there. Concavity changes right there, and then looks like concavity changes around there. This is just looking at it pretty roughly, so concavity changes right there as well. So these are x's are points of inflection, and then the dots are the critical points where it's equal to 0. Now I drew this kind of quickly, so this right here, this curve is really steep. You likely won't see something like this in the wild because the derivative of that would be undefined, but we'll just go with it like it's a really, really steep curve. This is definitely not to scale. This is just drawing it. So now that we've marked all of our points, what I'm gonna do is start plotting our points that we just marked off. So this one has a positive, this point of inflection is along a positive slope. So that's going to be above the x-axis, 0 right here for a critical point. Another point of inflection is below the x-axis because it's a negative slope. Then this right here is 0 again. Another positive slope. We'll say that that's pretty much equal to that one, that slope right there, this one. And now this is a very, very steep slope. So I'm just going to put it like right there. I mean, that's really steep. That's a decently steep positive slope. So I'm going to put that up there. And then another dot right there for 0. And then another negative-ish slope. All right, now simple enough. We're going to just nicely connect the dots. And I put a little bit of twist in this. How did I say this? I make these dots really curved. These vertices really curved near the end, but I mean, as long as you get the idea of it. There. So that is what the derivative will look like.